Alright, welcome to my video on what I call double replacement reactions. I've also heard them referred to as exchange reactions, and I think the proper name is metathesis reactions, and you'll see I've put both of those names up here. But I just have always found it easier to just call them double replacement reactions. The general form for what we're going to be dealing with here is where you have some sort of an ionic compound, a cation and an anion, and another one. And what happens is the positive from one bonds with a negative for the other, and vice versa. Please note when we do this, and you'll see I mentioned this here, basically you're going to combine the outer ions and combine the inner ions, basically the positive and the negative, and when you write the new ones, please always put the positive one first, because that's the general form. So it would look something like this. You're going to have lead nitrate, sodium sulfide. So you have these two compounds, and what's going to happen is I'm going to flip the cation and combine it with the anion here. So what will happen here is I'm going to have lead, and again, this is nitrates are -1, and I have two of them, so this must be lead 2 nitrate. So I'm going to write Pb, and then S. Sulfurs are -2 because the column they're in the periodic table. And then the Na will combine with the NO3, and please notice I'm going to put the Na first, and so this is going to be sodium nitrate. Sodiums are +1, nitrates are -1, so it's NaNO3. Now you have to balance it, of course, and I have 2 nitrates here, so I'd put a 2 here, which gives me 2 sodiums, 2 nitrates. I've already got the 2 sodiums, and I fixed my nitrates. Now, for my honors students, I'm going to want you to also recognize one other thing, and this is this stuff down here. I want you to recognize that the reason this will go forward is generally it's going to go forward because one of my products is going to be either an insoluble precipitate, a gas that kind of bubbles out of solution in some form, or it's going to be a molecular compound. The most common version of that is going to be water when we do acid-base neutralizations, which I'll show you down here at the bottom. I have some examples of that. So if I were to ask you to do that, though, it's really a rather easy thing to do. You just look at your two products, and you'd say, well, listen, I've got sodium nitrate. Which of these would be my precipitate? And if you come down here at some solubility rules that I have listed, and you can look these up in a lot of places. My students get these in a reference packet. You'll see that nitrates are listed as always being soluble, and sodium nitrate is indeed a very soluble compound, so that really will not precipitate out. However, my lead sulfide, if you'll look around, and oh, here's some sulfides down here, except for those of ammonium, the alkali metals, and calcium, strontium, and barium, you're going to find that sulfides tend to be precipitates. So what that means is this is going to be a solid, and I'm going to have to squeeze this in here, sorry about that, and then this you could list as still being an aqueous ion, and so then that would stay dissolved. Here's another example. Silver and chloride would come together, so I'm going to have AgCl. This is a positive one, this is a negative one. Let's look right away since we're talking about it. And again, this would be for my honor students. I would be looking for this. For my regular chem students, I just want you to understand how to flip them and then write the correct formulas. But chlorides are soluble except for silver chloride, lead chloride, or mercury or lead. So again, this is going to be my solid. And some people, I'll just do it a little differently here. Some people do it as a down arrow. And then my other compound here would be iron nitrate. Again, iron has 2 oxidation states, so this would be iron, since chlorides are -1 each, I've got 3 of them, this is going to be iron 3 chloride, so then I'm going to predict that I will get iron 3 nitrate, which means I would need 3 nitrates to cancel that out. In balancing, since I have 3 nitrates, I'm going to come over here and put a 3. I now have 3 silvers, so I put a 3 there, and I've got my 3 chlorides, so I'm in good shape there. Now my next reaction is going to be the reaction between sulfuric acid and barium hydroxide. This is an acid-base reaction. Acids and bases generally produce a salt and water, and by salt I mean an ionic compound. You'll notice that one is listed here. Neutralization reactions, acid and base produce salt and water. So what I'll have is here, I'll have the barium and the sulfate coming together. Bariums are +2, sulfates are -2, so it's simply BaSO4, and H2O, of course, is water. Now to balance this, I'd have to put a 2 there. Barium sulfate, again, if you want to look here, the sulfates are soluble except for those of barium. So again, this would be a solid and precipitate out. Okay, let's go through this next reaction. This next reaction is aluminum hydroxide and ammonium chloride. So my first product, of course, would be aluminum chloride, which would be Al. Aluminums are +3. Chlorides are -1, so it would be AlCl3, plus ammonium hydroxide. But now here's one of these cases, and this is one where specifically I'd like my honor students to be familiar with a couple of common situations. And one of them is if ammonium hydroxide is a product. If ammonium hydroxide is a product, what happens, it will split into ammonia and water. So first of all, you probably need to know, well, what is ammonia? And ammonia, if I've not mentioned it before, is NH3. So my products, rather than writing ammonium and hydroxide, or ammonium hydroxide I should say, I'm going to write ammonia and water. H2O. And then, of course, as far as going back to balances, aluminums look good initially. Chlorides, though, however, I have 3 here, so I'd probably start by putting a 3 there. That'll give me 3 nitrogens, so I'll put a 3 there. Oxygens, actually, I have 3 oxygens here, so my only place I have oxygens is right there, so I'd need a 3 there as well. So if I look at that, my aluminums are good, my chlorides, I have 3 of each of those, my N's are okay. These H's are all over the place. Let me check those. I have 3 times 3, I have 9, plus 6, that'd be 15. I have 12, plus 3 over here is 15, so everything balances out. So I'm in good shape there. The next one is copper 2 chloride and potassium carbonate, and again, this is just a slight variation on what I've been doing here. Notice I'm not giving you the formulas, so you need to kind of go back and be able to write the formulas that we've learned before. Copper chloride is simply Cu with a +2 charge. Chlorides, as we've said several times, are -1, so that's going to be CuCl2. Potassium carbonate, potassium is K, it has a +1 charge. Carbonates are -2, so I'm going to need 2 potassiums, so it's going to be K2CO3. And then I do my arrow. Now, as far as my products, basically things are going to switch around here, so I'm going to have copper carbonate, and again, this would be copper 2 carbonate, so that's going to be CuCO3 plus KCl. Because these are +1, these are -1. You can probably see right off the bat, since I have 2 Ks and 2 Cls, I would have to put a 2 in front of that to balance it. Now, as far as which one is going to be my precipitate, the carbonates are insoluble unless you have ammonium carbonate or an alkali metal combined there. So what's going to happen here is that the carbonate will be my precipitate. So this would be a solid coming out of solution, and chlorides, if you notice, are soluble. And so in this case, this would be an aqueous. And then for the last one, we have solid sodium carbonate is sprinkled into hydrochloric acid. Again, this is another acid and base reaction. Sodium carbonate is Na2CO3, because the carbonates are -2. We mentioned that up here. And that is reacting with hydrochloric acid, which is HCl. So my products would be Na and Cl, which you probably know is salt, sodium chloride, plus hydrogen carbonate, which would be H2CO3. But again, here is another one of these cases where I'd like my honor students to recognize it's a common situation where H2CO3 ends up being breaking apart into carbon dioxide and water. So rather than writing H2CO3, I'm going to write CO2 plus H2O as my product. And now balancing this thing, going back and forth here a little bit, I have 2 H's here, so I'd probably put a 2 there. I have 2 sodium, so I'd put a 2 there. My Cl's are okay, carbons are good, I have 3 oxygens and 3 oxygens, so I'm in good shape. So these are double replacement reactions or metathesis reactions, exchange reactions, or a variety of terms. Generally it involves flipping your cations and anions, and again, if you're required to or asked to, and teachers do this sometimes with different classes. They may want you to predict which one would be the precipitate, and for that you would need these guys over here, some kind of a solubility rules that you would then be able to apply and figure out, well, the insoluble thing, the thing that doesn't dissolve, that would be your solid, which some people do an S, some people do an arrow. Of course, you also sometimes get gases like CO2, and sometimes you get molecular compounds like water as well, which would also apply as far as allowing this reaction to go forward.